Hey everyone, welcome to the acoustics lesson for this class. Room acoustics is probably the one lesson where I'd say distance learning it really isn't going to have a big impact on learning the material and kind of figuring out what to do. Of course, experience will help beef this up, but room acoustics is a whole lot of theory, a whole lot of looking at what is in the room, what materials are used, and kind of treating it from there, which we'll get into. Now, whenever you get into larger spaces such as auditoriums or theaters, stuff like that, there's a lot more math that goes along into it. But recording studios and studio spaces are fairly straightforward. The basics, the definition that I posted here is a very long definition, but it's very thorough. Acoustics is a wide range of topics whenever we're talking about it. But the basic is it's the science of dealing with the production, effects, and transmission of sound waves within a room. But then you add on to that, it's also how sound waves interact in the room, meaning how they interact with the walls, how they interact with different pieces of furniture that are in there, how many people are in there. People totally are a very good audio dampener. But it also has to do with the materials used to build the rooms. What surfaces are used on the walls, on the floors. So the definition that I posted is very deep, but acoustics is also a very deep, kind of science, so to say. But yeah, we'll just kind of, I guess, move through it. The basic principle of acoustics, and specifically in recording studios, is the frequency balance of the room. And frequency balance is directly attributed to what's known as standing waves. Standing waves are whenever a wavelength equals the dimension of a room. So it'll add to itself, or it will kind of null out. In rooms we call it nulls, peaks and nulls. But it'll either add or subtract from the frequency range in that specific area. So, for example, with standing waves, if we had a frequency, I'm just going to throw it out there, that's 200 hertz, and say that's 18 feet long. Well, if your room is 18 feet long, then that 200 hertz sound wave is either going to add to itself or subtract from itself. So you're going to have a dip or peak in the frequency response in that, in that specific frequency range. So that's a standing wave. Room modes are similar, but it has to do with the harmonics of that standing wave. So the standing wave for the room will say, 200 hertz, which is 18 feet. So that 200 hertz, for all the multiples going up, you're going to also have standing waves. So at 200 hertz, at 400 hertz, 800 hertz, 1.6K, at each one of those intervals, you're going to have peaks and dips. So that's what a room mode is. Room mode is the multiples. Standing wave is the fundamental, so to say. This is also known as the resonance of a room. Resonances occur with just about any piece of material, and it has to do with with the dimensions and density, which we'll get into that a little later. But specifically for rooms, standing waves, which is the fundamental, and room modes, which is the harmonics, are the two biggest detriments to an even frequency response. So this is the worst picture I could find, but it also shows it best of what I'm saying. So here, the distance between the walls, 21 feet, which evidently fits 27 hertz exactly. So at 27 hertz, that's going to be the standing wave. And then the room modes are going to be the multiples, above that. So at 54 hertz, you're going to have a problem. 81 hertz, you're going to have a problem, so on and so forth. So these directly affect the frequency response of a room. It also depends, on which way is the sound bouncing. So axial room modes are the most detrimental to this. And what axial means is it's bouncing off two parallel walls. So you're either going to have the front and back, the two sides, or the top and bottom. So those are, when we're talking about room modes, axial room modes are the worst. There are other room modes. Axial, of course, is on the left. It shows it bouncing off two walls. Tangential, that word that starts with a T, that is going to be where it bounces off of three walls, I believe. And then oblique is where it bounces off of four walls. When we're actually talking about room modes, the worst are axial. Those are the ones that you're going to be the most concerned with. There are all sorts of room calculators online, which are fantastic, and if you look at it, it'll give you all the different modes for how many walls it hits off of. Sorry about that. Maybe I can edit that out. So this is kind of a 3D plot. I really wanted to pick this. I really picked this specifically so you can kind of get an idea of walking around a room and the frequency ranges. This is going to be the peaks and nulls. Obviously, at the back here, if you look at it, you have a very, very large peak against the back wall, which is fairly typical. We should be going over that here in a second. So looking at this is kind of what I mean by the frequency balance of a room. This is actually a really cool photo. You can kind of see the peaks and nulls in this room. I'm not sure if this is an actual like mathematical model or what. It might be. If it is, I want to get a copy of this software. It looks cool. But looking at this, you can see towards the back wall there is a very large peak, which is typical of rooms. I believe I get into that a little later with bass frequencies. But you can see right behind the listening position, there is a deep null. And it goes down about 50 decibels, which is huge. And this all has to do with room reflections and room modes and standing waves. The other big characteristic in acoustic design is the reverberation time. So if you ever walk into a building, specifically one that's very big, and clap your hands and listen to the reverb, that's kind of the signature of the room. And specifically dealing with acoustics, there's a principle called RT60, and it stands for reverb time over 60 dB. So what this is normally you'll do a pink noise burst in the room and then have a microphone that captures the resulting reverb. The reason you use pink noise is a flat frequency response versus white, which is I believe a flat level response. I could have that backwards. I'm not terribly sure. Pink noise is typically what you use to calibrate things, and I believe that is equal at all frequencies. They sound different. Who knew? The different noises sound different. But basically, what you do is you'll take a speaker and do a burst of this pink noise, and then you have a microphone that captures the resulting reverb. Now, how long it takes for that reverb time to fall below 60 dB gives you the RT60 time. So RT60 time is really important, specifically for live rooms, for places that are supposed to sound live, which is, amphitheaters, studios, not amphitheaters, because amphitheaters normally aren't in a room. Duh, you can't have room acoustics if you don't have a room, which is interesting. Outside has no room acoustics because it's not a room. But specifically for theater, orchestra rooms and stuff like that, the reverb time is very, very important to the overall feel of the room. Whenever we get into recording studios, whenever you look at the live room, we call it a live room because it's a bigger space, but it's also should be a little bit more live. Shouldn't be really, really live, but just a little bit more live. And then in the actual control room, we'll get into that. I believe also the control room should not be nearly as live. Um, the RT60 time, it can also be broken down into frequencies versus time. This is called a waterfall display, which I do have a picture of that. I'll show you that in a little bit. Um, it's really handy for figuring out room resonances and what to treat. So this is just kind of a graph of an RT60. So basically, you have the sound pressure level that energizes the room. You turn it off and you start measuring. And the time that it takes to fall below 60 decibels is your RT60 time. Um, this is a good little chart of RT60 times. It's really important to kind of get this right, depending on the use of the room. If you've ever been in some sort of conference and they have powered speakers and the room's just completely uncontrolled and you can't hear anything, it drives me crazy. But also, going up from the top, churches and cathedrals typically have the longest reverb time. And that really, draws into whenever you have a choir singing or something like that. It gives you kind of that ethereal feel, and makes it sound like, the choir is just everywhere and really intense. As you go down, theaters, office spaces should not be really reflective. Going down further, restaurants, specifically restaurants, if you ever go to one and normally there's a hipster restaurant that's all concrete inside and they didn't do anything. It's so annoying. But going down to what we care about, recording and broadcast studios, if you look there, the reverb time is very, very low. It's well under a second. Typically in control rooms, you don't really want any sort of RT60 time. We're talking half a second at the most, which is probably just enough to ring the room, and it kills it pretty quickly. So this is the RT60 waterfall plot. I say it's RT60. This really has to do with what rings out in your room. So it's a little weird to read. What you do here is it's the same sort of thing. You do a pink noise burst and you capture it, but you're looking. What you want everything to kind of decay similarly. So if you look against the far back, I believe my mouse show. So if we look up here, this is going to be the frequency along this back plot. This is going to be the volume level on the side. And then this forwards plot is the time factor. So if we're looking at this, how you read one of these is you do the burst and you're looking for uneven decays, right? So if we look at this, there's an uneven decay back here. We follow it down. So we have an uneven decay at 40 hertz and an uneven decay at, like, say, 90 hertz. It's actually pretty interesting because you can see this is probably 45. This is 90. This is about 150. So you can see that these are room modes. This has to do with the shape of the room, which is treatable because we can see this. So if we had this, we can say, oh, okay, well, we need to put something in there to absorb more low and low mid frequencies to get kind of a more even response. They're extremely handy. This is how professionals do acoustic plots, whether it's a recording studio or like an auditorium space. This is how they will do the measurements and the feedback that they get. So going on down, we not only have the acoustic resonance of the room, which is the room modes and standing waves. You also have that with materials. So each material used in construction has its own resonance. And it's based off the density of the material and the length of the material. So if you've ever been in like a car or been behind a car that is just pumping bass and it just hits that one note and the whole trunk just rattles, that's acoustic resonance or material resonance. Um, Beyond that, you also have sympathetic resonances. So you have material resonance and sympathetic. So a sympathetic resonance is going to be because something is connected to it. So if you have, a wall, let's say we have a wall that resonates at a certain frequency, but that wall is directly connected to the other wall, you're going to get some sort of sympathetic resonance off of that, some other vibration. And that's kind of the key to acoustics is you don't want things to vibrate on their own. I went the wrong way. You don't want things to vibrate on their own. You want everything to be controlled. And we'll get into how to control these different resonances a little bit later. The next part is the absorption coefficient. This is a fancy way of saying what frequency range and how much does a material absorb. So if you have something like hard brick walls, the absorption coefficient is going to be very low. In other words, it's going to reflect just about everything back. If you have, say, a lot of 8-inch insulation all the way around the wall, the absorption coefficient is going to be high. It's going to absorb a bunch of sound over a specific frequency range. The last thing that I want to talk about as far as construction, I'm going to show you some examples in a second, but is room symmetry. Typically, if you have a square room, this isn't a big problem, but if you have some oddball, room on some wing in the house that you decide to use for a studio, room symmetry becomes really important. Because it's with a square room, it is really easy to measure the room and figure out all your resonances and room modes. Once you get away from a symmetrical room, it becomes harder to do those calculations. And then it also can impact the phantom center of the listening position. So if the wall on the left-hand side is a different distance than the wall on the right-hand side, it's going to shift the image of the playback system one way or another. So now we're going to get into more of the construction. This has to deal with the material resonances and sympathetic resonances. The best way to build a recording studio, any sort of acoustically isolated room, is kind of the construction idea of a room within a room. So what you're doing is you'll have your room, and you'll basically build another room inside of it that is freestanding or that is decoupled from the other room. The idea behind this is the two rooms don't touch, so there's no sympathetic vibration. Normally, there's some sort of air gap in there, so it makes it harder for sound to travel through because they have to travel through one density of material, through another one, and then through a different density. So you're doing everything that you can to mitigate any sort of resonances and make it just harder for sound to travel and make it back into the room. So if you ever go to a built from the ground up recording studio and you're walking through rooms, look at the width of the walls. The walls can be sometimes they can be a little over a foot thick. Because of doing room within a room, and that is the right way to do it. I'm not saying you can't get by without, but that's the right way to do it. If you don't want your neighbors to hear you, it's the right way to do it. So this has to do with sympathetic resonances, is decoupling. So what decoupling is basically this goes back to the room within a room theory. Is you don't want two surfaces touching each other. Specifically, you don't want two rooms touching each other. So if you look at the first image on the left, this is a typical wall. You have studs in the wall, and you have insulation in between, and you have sheetrock nailed to the studs. So if you follow the sound wave on that, it hits the sheetrock, it travels directly through the studs in the wall and into the next room. That's what's considered coupled. Is one side is directly connected to the other side. The next two are just kind of different ways to decouple a wall. If you look at it, instead of just having one baseboard that the studs are, attached to, there's two baseboards. Instead of the drywall being attached to a stud that goes directly to the drywall on the other side, it doesn't. It just connects to the stud on that side of the wall. And insulation is put in between. This is the most common way when you build a studio to decouple walls. It's not quite as thick as the double stud walls, which is good, and it gives you just about the same amount of dampening as a double wall. You can do double walls if you have the space and the money. It does cost a little bit more. Cost is very interesting because that hugely factors into a recording studio. Because if you just walk into somebody's house and they have the conventional wall that's one side's coupled to the other, the sound transmission it's so much easier than if you have a staggered wall. So not only do you need to decouple the walls, you also have to decouple the floor from the floor. Because the resonance is between there. So the typical way that this is done is you'll have studs to raise the floor. If you're building this on top of another floor, you'll also have rubber feet below that. But above that, all these little black things that are on the studs are rubber. It's rubber. So what this is doing is it's decoupling the actual floor from the studs, and then if you put the rubber, decoupling pucks underneath, then you're also decoupling it from the floor again. And this is all for some sympathetic resonances. Material resonances you can get over a little bit. What they're doing here is you have the top portion of the floor, and if you look below that, the green line is actually what's known as green glue. And this is a very thick, rubbery glue. And that is to basically decouple the top from the bottom piece of wood. So you have multiple decoupling, techniques going on. And then below that, you also have more insulation. Insulation definitely helps to knock down some frequency range. We'll get into that. I think it's right after this. So tools. So after we have built the room and we've done all the decoupling we can, you have to start adjusting for room acoustics. The most important way to not to prevent room acoustic problems is the room dimensions, because the room dimensions inherently interacts with different room modes and standing waves. There's all sorts of calculators online. If you feel like going and looking at it, go for it. You can measure your room, pop it in there, and you can see what it says your room has. And this is also the main argument between square rooms and a reflection-free design, which I will show you in a second. Reflection-free design is complex. This also has to do when you don't have a symmetric room. It makes the calculations way more complex. So a lot of times people will go with a square room just because the room modes are known. It's real easy. Yeah, and actually that's literally what I said after that. So this is a reflection-free design. You'll see it in some studios. A lot of studios don't even bother with it. The construction costs are crazy because I'm going to get my mouse out here. So if you look, if this was a square room, as most rooms are, you're going to have a large portion over here that is just completely unused versus If this was a square room, you just have more space. So, like I said, standing waves, room modes are the worst, offenders as far as frequency response. And axial waves or axial standing waves, room modes, axial room modes. God, that is the right one. Axial room modes are the worst, reflection. So a reflection-free design tries to make it to where these speakers don't quite reflect and bounce off to your ear. So if you look at this speaker and it travels across and it bounces, the idea is to have the geometry so that it bounces behind your head. So that way, any wall that the speakers bounce off of, it bounces away from you because you want the direct sound from the speaker. Like I said, it's very expensive to build it like this, so a lot of studios just don't, and it makes it more complex. So there's two ways to deal with with acoustics problems. The first way is to absorb the sound. The second way is to reflect the sound. So this one we're going to talk about sound absorption. So what sound absorption is basically as sound hits something. The absorption is how much energy does this material absorb before reflecting it back. The most common sound absorption used in professional studios is basically it's called rock wool insulation. It is a dense insulation that is normally rigid. So when you see acoustic panels, this is what it uses. Now they're also known as broadband absorbers because they absorb across a wide range of frequencies. And the reason why specifically rock wool insulation is used is because there's been a ton of acoustics tests on these, and we know exactly how much they absorb for the given thickness and everything. So you can actually be pretty precise. The other material that you see a lot of times is foam. They call it studio foam or whatever. Studio foam is not nearly as thick. It's not nearly as dense. You aren't fixing problems below 1K. It's just not going to happen. The density is not there. The thickness is not there. So a lot of times when you go into a studio and you see foam everywhere, it's just for me, it's a huge downer. These people, they don't know anything about acoustics, is what it tells me. And there is one of the really, really big problems with acoustic foam, studio foam, or whatever, is this stuff is extremely flammable. Companies like Oralux treat their foam so it is I believe it's an actual fire retardant. Sound absorption panels, the acoustic insulation that they use in there, rock wool is a complete fire retardant. It will not catch on fire at all. And it's actually interesting to note. So rock wool, the reason they call it rock wool is they take, I don't know what kind of rock it is, but they literally take rocks and heat them up to melting point, and then they spin it out to where it makes threads. And that's what actually is the insulation, is it's melted and spun rock that is pressed together. So obviously it's not going to catch on fire. Studio foam, on the other hand, can be extremely flammable. The first time I found some, and the guy I was interning with, I was like, hey man, I got a buttload of this, a studio foam. And he goes, you should see if it's flammable. And I had never thought of that. So I pinched off a little piece, lit it on fire, and it went up so fast. So needless to say, if you have this covered all over your walls and something heats up too much, or somebody's smoking in there and it touches it and it just goes up, it's a huge, huge, huge safety hazard. Don't do it. And if you do have some and you want to use it, pinch off a piece, set it on fire, and see what happens. Anyways, I'll get off my high horse. Safety is super important, especially if you're running a business. So let's look at the actual thickness and density here. This is studio foam. This is of the egg crate variety, which makes me laugh. Just looking at it right away, you can see how porous it is, how not dense it is. The actual dips in it go down to, you may have not even half an inch of clearance. So obviously sound will travel through this fairly easily, except for high frequencies that are very short wavelengths. Acoustic panels will come like this. They call this a bass trap. It's a little different. It just has to do with the thickness. Interesting to note. So here's the acoustic foam, and then this is the acoustic panels. So these are all different types of rock wool. They all do the same thing, but the idea behind this is you get the acoustic insulation. It's also regular insulation too, so it'll keep your studio nice and cool for all the hot fire. So basically what you do is you have a wooden frame right here. You have the insulation that is pre-cut. You put it inside and you take this piece of fabric and you wrap it around and you staple it. If you buy these online, they're very expensive. If you make it at home, you can make them for dirt cheap. I say dirt cheap, $30 a panel. The thickness does matter. It will mess with the coefficients, okay, so that's a different slide. This, you can see the panels hung up in a room. This is kind of a small room for drums. But he's just kind of trying to control some of the reflections, and it looks really, really nice. Could you imagine if this was just a bunch of foam? It would just kind of look dinky and, not very professional at all. This is what I was getting with the coefficients. So this is going to be, I believe this is going to be a Roxol. Roxol is the company name, and these are the different sizes. So this is what I mean by acoustic coefficients. So if I can get my mouse. So what we have here is, this is the different density of the material. I believe it's 2 pounds, 6 pounds, and 8 pounds. Then we have the length, or the thickness in inches, millimeters, and then we have the 1/3 band octave frequency response of it. So, we can see that at 2 inches thick, this is 0.2, 0.61, 0.1, or 1, 1, 1, 1. If we go to a little thicker panel, you notice it starts a little lower. If we go to 6 inches, 1.3, and then it goes 1 basically all the way up. So you can see, basically, the closer you get to 1, the less reflection you have. The higher numbers is the less reflection. So if you're doing a room and it has a big bump at 125 hertz and you want to fix that, well, you can look at the coefficient table and go, well, if I do 6 inches, it really is going to help out that 125 hertz range. Now, but I don't have 6 inches to spare, so if I go with a denser material, I can come down, okay, well, with 1260 and 4 inches, I get about 1, which is pretty good. It's pretty good here, too. If I go to 1280, which is even more dense, I get a little bit better performance here. And then as you go on up, you can see what I mean by broadband. Like, it's depending on the thickness, you're getting everything from 250 hertz up. If you go with 2 inch, you're getting 500 hertz and up. And then different. Oh gosh, sorry guys. Dying over here. But this is what I mean by broadband. Now, if we were looking at acoustic foam, at 1,000 hertz, you would probably have about a 0.5. You probably have about a 0.6. And then over here, you may have a 0.8. So it's really only doing the higher frequencies. Broadband absorbers do much more of the sound range. So, next one. The broadband absorbers can also be used as what's known as bass traps. and this goes back, if we go back over here, the thicker it is, the lower frequency it will absorb. So bass traps, it's a longer sound wave. So bass traps will tend to be thicker than broadband absorbers. Um, Low frequencies also like to build up along the edges of rooms, in the corners, and along the top portion and bottom portion of the walls. So if you've ever been to a studio or even just in your room and you step all the way to the back side of the wall, you will see or you will hear a big boost in bass frequencies. And just like the image that I showed you at the beginning of this, where I was like, along the back wall, it's a little bit higher, you know, uh, boost. Anyways, you know what I mean. So bass traps are basically going to be the same thing as broadband absorbers, but much thicker. Um, there is one bass trap method that I want to go into. It's called super chunk. It's kind of what it sounds like. It is just stacks and stacks and stacks of this insulation on top of itself. And you can see what this guy did. He went up one wall and off across the top ceiling of that wall. This is really the only way to deal with bass frequencies in a room, bass buildup. There's some other kind of crazy ways to do it, but it's a lot more complex than this. So if you go to a studio and you see the corners kind of sectioned off like that, they're probably doing the super chunk method. And you can get the panels, cut it in half, and then cut it into triangles and stack that up, and that's how you do it. So really, the absorption, you can't do this with foam. The foam just is not dense enough. But the rock wool insulation will, it'll get the job done. And it's not nearly as expensive as it looks. If you buy it online and somebody made it for you, it's going to be expensive. But if you're doing it yourself, it's not nearly as expensive. So that's kind of it for absorption. That's kind of the way to remove sound. There can be a problem where you remove too much of the reflections, and you want to bring some of that back. This is where diffusers come into play. If we have two flat walls, two flat hard walls, you'll create standing waves. What acoustic diffusers do is it's a wall, but it's staggered. And the idea is to scatter the sound back in different ways so as not to cause standing waves. Diffusers obviously should be made from a hard reflective surface. Normally they are made from wood. You do see some styrofoam ones, which they work. They work better than nothing. But wood is the preferred method. They can also liven a room up. So if your room is a little bit more dead than it should be, you can put some diffusers in there and liven it up. It also has a very interesting way of making a room sound bigger than it actually is. So this is kind of the difference of diffusion. You can see it at the bottom. It scatters sound waves just around. Around too many parts of the room, not creating standing waves. So this is actually really interesting. I believe these are quadratic diffusers. The diffusers that you see, they actually use mathematical calculations to spread the sound back in the room in an uneven way. So you can see the top and the bottom. I believe these are both quadratic diffusers. But on the right-hand side, you can see how sound scatters back. And what you see at the top is you have less diffuser panels. So it scatters back, in a uniformly random way. And the higher order you go up, meaning the more notches on the diffusers, the more you get a more scattered sound pattern. Anyways, it's just real interesting to look at. Diffusers, if you don't have a very big room, you probably don't need diffusers. If you do have a larger room, diffusers can come in handy. So this is where we're going to start, I guess, applying some of this. So looking at a room with speakers in it, the big issue, right, are the axial modes, which is where sound bounces off of a wall and hits your ear. This is what's known as first reflection points. It's where sound bounces off one surface and hits you in the ear. This. If you remember our phase lesson, the recombination of the sound waves that are delayed in time are going to cause frequency peaks and nulls at different spots in the frequency range. So they are the main cause of bad frequency response in a room. Broadband absorbers are key to fixing these. Not only will it tighten up the frequency range, it'll also tighten up the imaging. So first reflection points should be treated in every room that you go to, and this isn't just the sidewalls. This is the ceiling also, the floor, depending on what kind of desk you have in there. A really cool tip to find your first reflection points, which I learned this actually online. I didn't realize you could do this. Is to sit in the listening position with your speakers up and how you want the room set up, and have somebody take a mirror along the wall and move it at the same height as the speakers in your eyes. And as soon as you see the speaker, that's your first reflection point. And then you can do this along the other side, and you can do it along the ceiling too, and you've actually pinpointed your first reflection points. They are the culprits for the bad sound. So that's the beginnings of fixing a bad sound. So those should always be treated. Here's kind of a diagram for it. You also have the back walls to worry about also. So anyways, try that. If you're treating a room, definitely use the mirror trick. You can look online. There's all sorts of tricks for acoustic stuff. And it can be done fairly cheap. It's the build out that's expensive. So this is an overview of kind of where to place absorbers, how to treat a room. This is kind of a basic setup. Studios, like I said, they're not theaters, they're not orchestral places, and they're typically we're all working with some sort of square or rectangular room. So this will be the typical setup here. So if you notice, we have absorbers along the back wall to fix the reflections there. We also have the first reflection coming off over here. And then on the back wall, there are also reflection absorbers to fix reflections there. Bass traps in every corner. I will say this about bass traps: you can almost never have enough bass trapping going on. So the more bass trapping, the better. Absorbers can get a little, tough, so to say. If you put too many of them, it can mess things up. So if we look at it, we have the first reflection points behind, sides, and the back. So these further back side ones are kind of there to control the back side of the room. In studios, specifically control rooms, there's kind of a thought to have it more dead in the front and a little more live in the rear. If your room's too small, don't worry about making it live in the rear. But if you have a pretty big room, on the back wall, instead of doing absorbers everywhere, you could actually do some diffusers to kind of increase the feel of the space, to make it kind of feel a little bit bigger. You would also, this little grayed out box right here is a ceiling absorber for that first reflection point. So anyways, this is a very good starting point. I believe that's it. Yeah. So that's really it for the acoustics. It's kind of dense. Don't forget that I have the these PowerPoint presentations. I will have it exported as a PDF so you can download it, so you can look at it. So when you take the test, you'll be like, all the questions were on that PDF. Sure would be handy. I will have that for download. Again, I hope you guys got something from this. Until you actually do it for yourself, it's just kind of theory. But once you actually start doing it, you can get some interesting results. Anyways, if y'all have questions, let me know. Thanks.